Oh, hello, everybody. Welcome to the SQL Saturday Croatia online edition. I'm going to do this in English because it's going to go on YouTube, so everybody can listen to the session irrelevant of their language. We'll talk about getting to know SQL Server encryption capabilities. So basically, we'll go over some stuff where that's not that used in SQL Server. I don't know why, but we'll go through that. A bit about me, I'm from Slovenia, just your north neighbor. I'm an MVP for the data platform. I work with SQL Server and .NET for like 20 years now. Lately, I've been doing some work in Swift. I developed an add-in for SSMS called the SSMS Toolspec. I wrote a few books, and that's about it. Okay, so what we'll talk about is, first we'll do a quick terminology refresher. We'll talk about what certain terminology means. Then we'll talk about transparent data encryption, and then we'll talk about securing communication channels with SSL and TLS. We'll take a look at symmetric and asymmetric server encryption, and then we'll look at always encrypted. Okay, so quick terminology refresher. Basically, what we do is we use cryptographic functions. For encryption, we use either symmetric or asymmetric encryption. With symmetric encryption, you encrypt and decrypt your byte array with a single key. You have multiple algorithms. They're DES, triple DES, AES. Basically, DES and triple DES have become pretty much obsolete, and the most commonly used one is the AES. If anybody has any questions, they can ask just during the session. I don't know how that works, but I'm sure the organizers can let you know. When we talk about asymmetric encryption, though, we have a public key and a secret key. So you have to have two pieces of the puzzle to unlock your message, right? So you encrypt the message with either a public key or the secret key, and you can decrypt it with the other one, right? But compared to the symmetric encryption, is much slower, and it's usually used to exchange symmetric keys. So basically, if you have a SSL channel, what they do is they create a symmetric key to encrypt the data with, and they exchange that symmetric key between you and the server using asymmetric encryption. That's also, by the way, how Always Encrypted works, which we'll take a look at. So encryption is a two-way function, right? You can encrypt and decrypt. Now hashing is a one-way function, and it's irreversible. So if you have a text and you hash it, there is no way that you can get that original text back easily, or hardly. There are also quite a few algorithms like MD5, SHA-1, SHA-2, and SHA-3. MD5 it's still in use, but it's going out of use slowly because there's a lot of rainbow tables for all kinds of hashed values for MD5. So they're mostly used to hash passwords. So if you have a password that's like 5 characters long, you have all available MD5 values already available online. SHA-1 and SHA-2 and SHA-3 are, of course, much harder to calculate. So one thing to note here, though, is that from SQL Server 2016, all algorithms other than SHA-256 and 512 are deprecated, meaning that for any new development work, you should use those two algorithms. All others, don't use them. Because you never know if they're deprecated, you never know when Microsoft might remove them from a future version. And then you have something called an HMAC, which is basically a hash-based message authentication code. Now, what this does is it verifies both the message integrity and authentication of the message. So the way it's done is you take your key and you take your ciphertext and you prepend the key to the ciphertext, and then you hash that. And then to that hash, again, you prepend the key. And then again, you hash that, and that gives you the HMAC value. Now this means that with the first hashing of the key and ciphertext, you verify the message integrity because nobody knows your key, or nobody should know your key. And when you add another key to it and then hash that, you authenticate it as yourself. You authenticate the message that it hasn't been messed with, right? Now, there are two ways that you can encrypt things, deterministic or random. in deterministic encryption, you have a plain text and you encrypt it, and you always get the same ciphertext back, right? So it doesn't matter how many times you try, you always get the same ciphertext. Now, this is good for database use in a way that it can be indexed, it can be joined, you can group by it, or you can look it up in a singleton lookup. So if you say where your column equals some encrypted value, you cannot do where something like or where something is greater than or lesser than. So just singleton lookups on equality. Of course, because it's always the same ciphertext, it's vulnerable to statistical frequency attacks. Now, what that means is, if you say, for example, have a table of countries, and you link those countries to your, say, order items, and you do most of your sales to, say, Germany, for example, an attacker might realize that your encrypted value is Germany just from the amount of that of usage of that encrypted value, because they might know your company, and they might figure out, okay, so this is Germany, so we eliminate one value, and then they can in this way they can eliminate other values and find out what the encrypted values actually stand for. It's basically guesswork, right? They cannot decrypt the thing, it's just guesswork. So don't deterministically encrypt values that have a small distribution of the values. So true, false, male, female, countries, territories, etc. And in this graph below, you can see a typical distribution of letters in English language text. And you can see that letter E is the most used letter in English language. Now, randomized encryption, on the other hand, takes a plain text, and every time you encrypt it, it always comes back with a different ciphertext. So no two values are alike ever. Statistically, they look completely random. It cannot be practically reverse engineered. The values that are public are the ciphertext, so the encrypted value, and the IV. Now, the IV is something called the initialization vector, because the way it works is it splits your message, so not a non-encrypted message. It splits it into chunks of same size chunks, and encrypts the first chunk, and then puts the value, the encrypted value of that first chunk, puts as the input for the randomization engine into the second chunk, and so on and so on and so on. But what to put into the first chunk? So that's what you do with the IV. You generate a random initialization vector. It's just a byte array, and you put it into the first chunk, so that you can encrypt it and feed it to the next chunk. But of course, that means that you cannot index on it, you cannot join to it, you cannot group it, because it's just random. And if you look at how that looks in images, for example, you have an original image. The middle image is encrypted using deterministic encryption, and the image to the right is encrypted using the randomized encryption. Now you can see that even though the penguin in the middle image is encrypted, you can still figure out that it's a penguin, right? So that's basically a visual representation of statistical frequency attacks. Okay, so that's a quick terminology refresher. Let's talk about transparent data encryption. Now, a few people I've talked to about transparent data encryption thought that this, because it says transparent data encryption, they assumed that it would encrypt your data even across communication channels. So this is not TLS or SSL, right? This does not provide encryption across communication channels. The data is encrypted actually when writing and reading to and from disk, right? So the SQL Server engine, the way it works is you have a file on disk, and that file is encrypted. And when the SQL Server reads the data from that file into the buffer cache, it decrypts the data pages read from disk. And then when it goes to write the data page from buffer cache or from the transaction log or wherever it goes, it encrypts before writing to disk, right? So that's where the layer of encryption works. So anything in memory on the SQL Server is in clear text. So you might ask yourself, what's the point then, right? The point is that if somebody steals your physical drive with the data, but not the disk with the OS installation, because it uses the data protection API from Windows, and if somebody steals your OS with your disk with the data, they can reverse engineer your keys. If you're interested in this, search YouTube for breaking Microsoft SQL Server transparent data encryption. It's a really nice video, about 20 minutes long, and the guy in that video basically reverse engineers the key, the TD key from the Windows OS, and basically cracks open the transparent data encryption. That's why I always say that you should always have your physical drive somewhere else than your OS installation drive. Now, the thing is, it's not that realistic, right? Because you have one machine, you have a SAN or something. So a lot of people are just saying that it's just to check a box on the requirements and that's it, right? That's why I always suggest to use the hardware security module for TDE, because the hardware security module is completely separated from your OS, right? So even if they steal your OS disks and data disks and everything, and they don't get your HSM, they won't be able to decrypt it. So in combination of these two, it works really well. And it's really simple to enable. You have to create a master key encryption, master key for the TD encryption with a password. You create a certificate with some subject if you want. And then you simply say create database encryption key with algorithm, encrypt by server certificate that you've created, and say alter database, set encryption on, and that's it. And if you want to remove it, you just say set encryption off, and it will stop encrypting. So it's really not hard to enable. Okay, so secure SSL and TLS connections. So if you want to enable SSL for your whole server, it's very easy to do. And I always say that if you want to mess with your developers or with your security people or even IT people, just on your SQL Server, just say, I want to require SSL for every connection and see what breaks. Because not a lot of stuff support, there's still a lot of legacy stuff out there, different applications that aren't able to use SSL or TLS. But if you want to do that, if you want to enable SSL for every connection, if you want to require it for every connection coming into your SQL Server, what you do is you install a certificate on the SQL Server machine. It can be a certificate authority certificate or a self-signed certificate. You say in the configuration manager, you say force encryption equals yes, and then you don't have to change anything on your clients. So if your client supports SSL and TLS, they will connect. If they don't, it will throw an error. Because why? The way it works is your server says, okay, I have this certificate that I want to encrypt all connections with, and this certificate is composed of a public key and a private key, right? And the server, the SQL Server, will always keep their private key, but they will send. So when the client creates a connection, it says, okay, I require you to have a encrypted connection. Here's my public key. Use this public key to encrypt the data. So to encrypt the symmetric key for the data transport, the way we talked before, the way it works. So the client will now have that public key, and they will encrypt basically the data, and they will start communicating through encrypted connection. Now, if you want to say that I don't want to have all connections encrypted, I just want to have certain client connections encrypted, you say on the SQL Server that encryption is an option, but on the client, you have to say encrypt is true in the connection string, and you have to trust the server certificate. So you have to take the public key from the SQL Server's certificate, and you have to install it on the client, because otherwise the client doesn't know where to get that public key, right? If your connection is encrypted, you can check in DMV, sysdm exe connections encrypt option. If it's encrypted, it's 1. If it's not, it's 0. You can also encrypt it with IPsec, so IP security, but both client and server OSs must support it, and it basically works out of the box. To enable it, basically you go into SQL Server Configuration Manager under SQL Server Network Configuration Protocols. You click on the properties, and you have in flags, you have force encryption equals yes. And in the certificate tab, you choose your certificate that you have to install on your SQL Server before choosing it here, of course. And that's pretty much it. Now, if you want to enable TLS 1.2, which is the latest one, usage of TLS less than 1.2 is not encouraged anymore. So they are trying to, Microsoft, Google, Facebook, etc. They are trying to move everybody to use TLS 1.2. SQL Server 2016 and up supports TLS 1.2 by default. There's nothing you have to do about it. For other versions, though, if you're still using 2014, 12, 2008, 2008 R2, there are various steps you have to take. And for those steps, to learn what they are, go to this link, which will guide you through everything from 2008 onwards to 2014. Yeah. Okay, so next up is symmetric and asymmetric server encryption. For asymmetric encryption, we have a few functions called encrypt by asymmetric key, encrypt by certificate, sign by asymmetric key, and sign by certificate. Now, both certificates and asymmetric keys are basically wrappers over RSA keys. RSA is the algorithm for generating public-private key pairs. As I said, it's slow. It's used for encrypting small data. As I said, symmetric keys that are used to encrypt the communication between two points, you encrypt those symmetric keys with this asymmetric key. For symmetric encryption, though, you have encrypt by key and encrypt by passphrase. Now, encrypt by passphrase uses triple DES, so don't use it, right? Because DES has been deprecated a long time ago. It's easily, well, not easily, but relatively easily to crack, and triple DES is simply DES applied 3 times, right? So not that hard to crack in the end. Now here's the thing. Here's the problem with potential problem with symmetric encryption, right? So this is your standard table. Now you have 3 people: a junior DBA, a CFO, so chief financial officer, and a DBA, and each of them has a salary. Now you don't see the salary because it's encrypted, right? Now, out of our professional experience, we know that usually the junior DBA has the lowest salary, the DBA has the median salary, and CFO usually has the highest salary out of these 3 options, right? So how can I attack this as an attacker, right? What I can do is I can say update junior DBA salary to the value from the DBA salary, right? So in the first row, I will have the value for the salary. I will have the value DDF, GES, etc. Right? Who will know? Nobody will know. This value will be then decrypted, and junior DBA will have the same salary as a DBA. Right? This is a potential attack vector. So how do you protect against this in SQL Server? Right? What you have to do is you should always use an authenticator. This basically prevents this kind of attack, which is called whole value substitution attack. Now, what this does is when you encrypt the salary value, you say, I want to use ID of the row as my authenticator, right? So it will say, feed into my encryption function as the first parameter, my salary, and as the second parameter, my ID. So the parameters will be the salary of the DBA, whatever it is, and 529. And if I then say update junior DBA salary with the salary from the DBA row, when it gets to be decrypted, it will also take as input parameter the ID, but this will be the 352. And because the 352 is different than 529, it will fail the decryption and it will fail the whole query, right? So that way, you have to decrypt the same way that you have encrypted it with. And this ID is in the encrypt by key and encrypt by passphrase functions. which I'll show you later in a demo. So one problem with encrypting data is that you lose the ability to search through it, right? If you have, say, 100,000 rows and you have encrypted column inside that table, if you want to search through that column, you have to decrypt all of the values and do where something equals or like or whatever, right? But you have to decrypt everything. So how to make this faster? What you can do is you take your message, so basically your unencrypted value, you encrypt it and you get the encrypted value, right? Then so now you have the encrypted value of your column, right? Then you take your message, so your unencrypted value, and you create a hash of it. So you just hash that unencrypted value, and you get some byte array. Now you convert that byte array to integer, because it is integer in the end, right? You convert it to integer. And then you say, I want to partition that integer, right? So you say, for example, I want to have 1,000 buckets, 1,000 partitions over my data. And you say, my partition is I modulo 1,000. And every instance that goes, that says I modulo 1,000 equals 0 will go into one partition. All of them saying equals 1 will go into another partition, right? And then you can use that partition, that P value, you can use it in a where clause to partition data, right? So you basically minimize the search area of your data. And I will show you how to do this in a demo. And the best of all, P can be indexed, right? So let's see how this works. So what I have here is 5, okay? I have a table of credit cards. I have 110,000 credit cards in this table. Now these are fake credit card numbers generated online without issue. They are all valid and everything with different credit card verification checks, but they're fake credit card numbers. So we will be looking for this credit card number. Let's see if it exists. It does exist. And observe what is its ID. So the ID is 99,999. Why? Because this ID is at the end of the table, right? So we have to read the whole table before we get to this row, right? Okay. So what I'll do is, if I say, so observe the columns that I have. So card ID, issuing network, so it's a MasterCard, it's the card number, and I have the encrypted value here and the hash group, so that's that P, right? So these are null, both null, because we will populate these values. So now let's see how many credit cards we have that end in 8007, because we have, just a moment, we have 22 rows. Why? Because usually credit card processors have the last 4 numbers saved in a special column, right? But we don't want that. We want to make this proper, right? Okay. So what we'll do is we'll create a temporary symmetric key. Now, I don't know if you knew, but you can create temporary symmetric keys which are valid just for this session, right? So just like 10 tables. So when I close this down, they will go away, and this way I don't have to drop them or anything. So I will create a symmetric key I will encrypt it by password because it's easier for demo purposes. But it uses triple des, and I said don't use triple des for the password. Okay. We have created a symmetric key. We'll open that symmetric key, okay, and then we'll say encrypt by key GUID. So that way we identify our symmetric key. The column we will encrypt, and 1 as to use the authenticator, and what we will use. So we will use the card ID. Right? Now let's update that, and this will take a few seconds. So notice that it takes we have to first search for it. So the way we search for it is we'll say select, decrypt the actual data, and then look for that credit card number, right? So if we say like this, and we have the decrypted credit card number, encrypted credit card number, right? So we have these two match, credit card number and decrypted credit card number, these two match. Now let's check how long it took to do that. So we did 2,731 logical reads. It took about half a second, right? So remember those numbers if you can. So about 3K rows and half a second, right? So how do we partition this? So we will create that function that we talked about when I showed you the flow of things to do. So what we'll do is we'll have the string as input and divisor as input. So divisor is 1000 in our example in the PowerPoint presentation. The string is our input value that we will group on. So what we'll do is we'll hash the string. We'll create a hash, we'll create the result, put it into the integer, and if divisor is larger than 0, because we have to have it larger than 0, we'll make a modulo between the two values and return the modulo value. So we will return 1 or 2, so which bucket it goes in, right? The ID of the bucket, basically, in which this unencrypted value will go in. So we will hash it. So we will create the hash group. Now notice that the input value for the group data function is the card number, so the unencrypted value. This has to be the unencrypted value. And our hash bucket means we'll have 1000 buckets. 5. Okay, this is done. And let's create a simple visualization of the distribution. So you can see that they are pretty equally distributed, right? So we have the same, approximately similar amount, similar number of credit cards or rows in each group. You can see, right? There is no group that goes far to the right or far to the left. They're all in there somewhere around the middle. Okay. So now we will check our card number, and we are in the card number hash group number 760. So this is good. Okay. So let's search for it. So we say we have the same query as before. We just add our partitioning function to check what our calculated hash group is. So we have to calculate our hash group on our credit card number, right? So the input here is the credit card number, so we don't read through the table in this part, right? So this is the input value for the comparison to the card number hash group. And then once we lower the amount of rows that we have to check or decrypt, we say decrypt by key, right? So how long will this take? Let's see. Okay, it took a bit. Now check this. It made the same number of reads, so 2,731, but it took 1.5 seconds, right? Now why? Because I didn't have an index on it. Right? So if I add an index on it, so I add an index on the card number hash group. Okay. And now, same query as before, it will be instantaneous. Right? So we have 387 logical reads and basically 2 milliseconds of elapsed time. Right? So compared to 1.5 seconds, this is a huge improvement, right? And if you have a server that is constantly getting hit with credit card numbers, credit card number checks, if you reduce your query time from 1.5 seconds to 0 milliseconds, you will be a hero to your company, right? And you can see that we have, for the top 10, we have different card groups, right? Okay. Next up, so that's for the symmetric encryption. Now, next up is always encrypted. I always ask when I do this live, how many people use or have even evaluated always encrypted. And I usually get about 5 to 10 hands going up. And the people who have used or evaluated it are always from the same the same industry. It's either healthcare, banking, or insurance, right? And it's understandable because if you have the data encrypted, it prevents you from doing any kind of analysis on them, right? And you know how today is. The data is the heart of the company, and you have to analyze that data to have some kind of business value out of it. With symmetric and asymmetric server encryption, you hold the key. So you can decrypt all the data that you hold on your server, and you can still do that analysis. With Always Encrypted, you cannot do that. Because with Always Encrypted, the client has the key. You, as the owner of the server, don't have the key to decrypt anything. So I'll give you a few seconds to read this, because it perfectly illustrates how the encryption world works. Okay, so basically what the comic is about, right, is you on one side you have IT, and they're like, oh my God, we have to solve everything by technology, but sometimes it's best, in cases like this, it's best to use old-fashioned violence. Even though, you know, that's how it goes. So Always Encrypted works with a single algorithm. The name of the algorithm is long. It's called AEAD AES 256 CBC HMAC SHA 256. It is used both for deterministic and randomized encryptions. The way it works is you have two keys. You have a column master key and a column encryption key. The master key, the column master key, is never stored on the SQL Server. So you have a column of your unencrypted data, and you say, okay, I want to use Always Encrypted on it. You generate the column encryption key, you encrypt that data in your column with the column encryption key. Then you take that column encryption key and you encrypt it with the column master key. And the column master key is what the user has. So you don't have the column master key. So you cannot decrypt the data stored on your SQL Server. And this, of course, prevents the DBA with admin permissions to check sensitive data of your customers. So it's a column level encryption setting. You can enable it via connection string or in the app itself, and I'll show you how to do that both. It requires .NET 4.6. You can have various key store providers like Azure or your certificate store on your computers. But if you want to have custom key store providers so that you can create your own, you have to use .NET 4.6.1. Also, if you want to have support for bulk copy inserts into SQL, loads into your SQL Server, you also need to have 4.6.1.NET. So how it works? How does it work? On your client, you have the ado.NET driver, right? And you say, select name from customers where SSN equals some value, and the value of that parameter is not encrypted, right? So because it's on the client, your client knows its data. So it puts in an unencrypted value into the query. That query is sent to the ado.NET client driver. Now the client driver has been upgraded to know about Always Encrypted and says, okay, here is the query using Always Encrypted. I need data to be able to encrypt it, to be able to encrypt that unencrypted SSN value, right? So it says, okay, SQL Server, I'm gonna need the data that I need to deal with this query. And it will download the blob from the SQL Server in which there are column encryption keys. Then it will load that column encryption key into its code, and with the column master key that the client has, it will be able to decrypt the column encryption key. Sorry, encrypt. No, it will be able to decrypt the column encryption key to encrypt the value to send to the server. So you can see that the value, the query that is sent to the actual SQL Server from the client is select name from customers where SSN equals parameter, and the parameter is the encrypted value, right? So the unencrypted value is never sent to the SQL Server. Now on this encrypted value, the SQL Server says, okay, singleton lookup, says, okay, I have one row returned, or multiple rows, or however many there is, and returns the encrypted result set back to the ado.net driver. Now the ado.net driver has all the data it needs to decrypt those results. So your client is kind of bound by this trust boundary, right? So the unencrypted data never goes outside of this boundary. So let me show you how that works. So we will have I've already built this database, so we'll just have a AE demo database. The column master key is in my certificate store, but this can be whatever store you support. The column encryption key is also created by using encrypted value, and I've converted the actual encrypted value with PowerShell to the byte array. And then in my table called users, I say, okay, I want to have the user SSN column encrypted with always encrypted. So I will use deterministic encryption type in this case. I can also use it. I can also use randomized, but if I want to be able to search on it, I should use deterministic. The algorithm is just one, and column encryption key is end-to-end sec CA key, so this one, right? And the way to do it is I will insert the same as before, but the thing is, for always encrypted to work, the collation has to be bin2. You have to have a binary collation on your column, right? Because it works only with binary 2 collations. That's a requirement. And then let's check. I already have those two values inside, but you can see that I have encrypted value inside them. That's because I didn't run this query with always encrypted available through the connection string. So if I say connection, change connection, options, always encrypted, enable always encryption column, connect, use AE demo, and I say again, select from the table, you can see that now I have both columns decrypted, because SSMS knows, as it should, that if I use the always encrypted option in the connection string, it will successfully decrypt this data, right? So if you want to use always encrypted, you should have that in your connection string. Now let's see the code, the .NET code that this works on. So we will have the best. Let's just run profiler first. Connect, run. Okay, we don't need this, just to show you what's happening. So what we'll have here is the best demo app you've seen ever. And when I click no key, it will simply do select from users, right? So no key, it will return two result sets, two rows, sorry, and it will have the same values as we saw in SSMS when we didn't use always encrypted. Now, result set only option, if I say result set only option, I haven't done any filtering on it, so I still got 2 rows back, but I got decrypted values back. The way this works is, I have a connection string here, but I don't have any always encrypted settings inside the connection string. That's because I wanted to do it from the code, because you can also set that from the code. So I say here, SQL command column encryption setting is result set only, and I put that as input into the generation, into the constructor of the SQL command, and then I do the same thing as before. And what this will say is, only decrypt the result set that I get back. Don't send any encrypted data to the server, right? So don't do any filtering. You cannot use the where clause there, right? Now, if I say full always encrypted, I will say enabled, completely enabled, and I will create a parameter, and this will work the way that I shown on the image. So if I say 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, and I say full AE, because I do where user SSN equals user SSN, it will return the correct value. Now, how does it know when to do that? If you check the profiler, you will see that for this last query, I said, okay, where user SSM equals the parameter, and this parameter is encrypted. Now, how does the client know what and how to encrypt? Well, the client, the ADO.NET provider, says, look, I need the data for this. So SP described parameter encryption for this query and which column, it will return the, we can actually run this in SSMS. And show you what it does. And it returns the data about your column encryption keys and column master keys. So you can see the column encryption key version, metadata version. So if you update your keys, this will upgrade. Column encryption key, encrypted value, provider name, master key path, right? So it has the path, but it doesn't know what the value is, right? So if you have a custom key store provider or Azure Vault, this will be the path to that Azure Vault, but not the actual password, right? So that's the way this works. So this is the always encrypted, and if I say something else, it will not find anything. And if I go vice versa, it will show Chuck Norris. Now, the way this works in SQL servers prior to 2019 is the way I've shown you. Now, in 2019, they've improved the always encrypted by a lot. What they've done is they created something called a hardware secure enclave. So this is not the, Microsoft didn't come up with this. This is on the chipset. It should be on the chipset. But what it enables you to do is to create a secure enclave on your SQL Server. Now, this secure enclave is either a hardware enclave or a software enclave. Basically, it's a part of memory that is not available for access to any of the outside processes, right? And the way it works is you have, again, the enhanced client driver, so the ADO.NET. On the client, it's the same as before. But if you send in a like or range comparison, so if you say where column like percent company percent, right? So you do a like comparison, it will say, okay, I will take that column from my table and copy all of the encrypted values in that column, which are all of them, into this secure enclave. Then this secure enclave will connect to my driver, to my client driver directly, so it won't go over through SQL Server's buffer cache or anything like that. It will create a direct secure channel to the enhanced client driver on your client, and it will share the key, the master key with it. So the master key will be sent to the secure enclave, and in the secure enclave, the data will be decrypted, checked, pattern matching whatever query you want, whatever where condition you have, and the row IDs, so not the decrypted values, but just the IDs of the rows will be returned back from the secure enclave to the SQL Server, right? And then it will get destroyed, that memory space. And the SQL Server will say, okay, I have these IDs, and I will now send those IDs back to the client. Of course, with the IDs, you can send other data if you wish, but that's the basic principle of it. Now, setting this up is huge. I have a whole 1 hour session on this Always Encrypted too, and I've done the demo for that when it was still in CTP, and I had a session at another conference last year, and one day before the conference, you should never do this, I upgraded the version to the SQL Server to the RTM, and they changed something, and my whole demo just went boom. And I couldn't recreate it if I wanted to in one day. So it takes a bit of time to create everything. So, but in the end, it works nicely, and you can search on it on encrypted values. Now, the issue that I see here, potential issues, are how secure are those secure enclaves, right? You still have to share your master key with the memory space on your server, right? Sure, it's through a secure channel, but still, right? There's always bugs in either CPUs or like Spectre or something, or in SQL Server, etc. So yeah, and with that, we've come to questions. I think we're just about on time. I don't know how questions work, but if you have questions, let me know. And if not, I'll leave it to the organizers to end this session. I'll just say thank you for joining me, and that's it.
I would like
Yes.
a question. Please.
Go ahead.
I would like to ask if the secure enclave performs any type of caching, or it simply directly destroys after the query is finished.
So the question is if the secure enclave is directly destroyed. So as far as I know, it is. The memory space is one-time use, and it gets created especially for the query, and then it gets destroyed especially for that query. As far as I know, if this has been changed, I don't know. That's it for the answer. So if there are any questions.
Okay, if there are no more questions.
Okay, thanks.
Maybe one more.
Okay.
Yeah. So I'm a little bit confused. I was confused in one moment when you said that server will accept query from the client with already encrypted value, and he will return something. I mean, it was related to Always Encrypted feature. So I was always thinking about that in a way that Always Encrypted will deal with some columns, and you will query by non-encrypted columns, and then you will decrypt on the client. So
yes,
I'm actually confused. What did I miss in this explanation? Okay. Your explanation, if you can just elaborate.
Yeah, sure. So on your client, because the client knows the master password, everything is decrypted, right? Now, when the client sends the data to the SQL server, that data gets encrypted because the client has the master password, right?
Yeah.
Then the server has only encrypted values, makes the search with encrypted values, so it's a singleton lookup because you can do that, and returns back the rows with encrypted values. And when those encrypted rows get back to the client, the ADA.NET provider decrypts them and returns the decrypted value to you.
Okay, so I was correct. So I just
yes.
Yeah. Okay. Yeah. Thanks.
Sure. So that's the whole point of Always Encrypted, that the unencrypted value never goes into the SQL server.
Yeah. True.
Basically,
okay.
it never goes outside of this trust boundary.
Yeah, and just one more comment. So you mentioned .NET Framework 4.6 and 4.6 something. And what about .NET Core? I mean, Always Encrypted was not available for Entity Framework Core until version 3, I think. So, and now it's available, but actually I tried a few times. It's very hard to find some examples or something. So do you have some experience with .NET Core?
None.
No, yeah.
None. I haven't done a single project in .NET Core yet.
Okay.
So it's not that it's not that much used for the new stuff. I mean, for old stuff.
Okay.
So yeah, no, sorry.
Yeah, thanks. And this lecture will be published somewhere, right?
I think so, yes.
Yeah, I have to.
Yes, it will be.
Yeah, I have to review a few times.
Okay, cool.
Any more questions? No? Thanks, Mladen, then. Great lecture.
Okay. Excellent, thank you.
See you on the raffle.
Yeah. Bye.
Thanks a lot.
Thank you.